welcome to the Stellar Structure and Evolution revision lecture, which is being done as a video due to the COVID-19 pandemic, which has also, of course, changed the way that you're going to take the exam. And indeed, from the practice exam, it has the old cover sheet saying 2 hours, where you have, fortunately for you, much more time than that, about a day. And you'll also have access to the lecture notes, so that will make life much easier. Although I do, of course, appreciate how disruptive this time has been. Okay, so the important thing to note from the cover page is that the exam is set up the way that it normally is, where you have section A being capped at 20 marks and section B being 30, and then you add 20 plus 30 and you multiply by 2 to get 100. So in section B, make sure that you only answer one of the questions, and we'll go through this practice exam. Now, this isn't as relevant for you because you have access to the lecture notes, but it's still useful to have these relations listed within the exam. So I'm not going to go through every single question because the solutions are being provided on Keats in a nice typed up format, but it's worth going through a few of them to show what I'm expecting in terms of marking, and also just to get a feel for what these questions are really asking. So in section A, again, it's capped at 20. Now, since you have enough time, it's probably worth answering every single one of them. But there's actually 30 marks, and the most you can get is 20. So if you get 29 out of 30, you'll still only get 20. In that way, you could skip one or two if you're confident, but might as well do them all on the real exam. So I'm going to choose 3 from section A to go over. And in fact, I needed to make a small correction to 1.7, and I'll go over that now. And then we'll look at 1.8 and 1.6. So 1.7 is asking us to think of an unrealistic case where we have a constant density for a star. We know that stars actually are much more dense in their core, and then as you get further out to the surface, they become much less dense. But of course, things are much more mathematically simple if you just make a simplification that it's a constant density. In that case, you get the gravitational potential, which is given to you, of the minus 3/5 gm squared over r. And then what you can do is, using this assumption and also assuming a pure hydrogen composition, which again we know is not very accurate, that you can get a relatively simple relation for what the temperature should be in terms of the total mass and the total radius of the star. So let's look at that one. So as you'd be writing down in your exam notebook, which you're going to scan when you submit it, you put the number 1.7, and what I'm looking for is, of course, the relevant equations that you're using, but it will help quite a bit if you can include at least a few words describing what you're doing. So, for example, if we're starting with the given potential energy, we can write that down for the gravitational energy. And that was given to you as EGR is minus 3/5 gm squared over r. And now we can think about how do we relate that to a temperature? And since we have this situation where the different layers of the star are in thermodynamic equilibrium. And in fact, we're simplifying to consider a constant density throughout, so then might as well use the virial theorem to relate the gravitational energy to the thermal energy. So again, if you just write out virial theorem, it gives me a better idea that you know what you're doing. And that is that the thermal energy is equal to minus 1/2 the gravitational energy. And what is that thermal energy? Well, we also have a relation for that. So ETH is 3/2 nkt, where capital N is the number of particles. And here the assumption for it being completely hydrogen makes it relatively easy, because then we don't have to worry about the composition, the mixture of different masses of different particles. And we think of each of them having the mass of hydrogen. So if they each have the mass of hydrogen, then you have a certain number of them, and those all add up to the total mass. So in other words, the total mass divided by the mass of hydrogen is going to be the number. Okay? And so now we can plug everything into the virial theorem. So this now gives us 3/2 times big M over mh multiplied by kt, and that's equal to minus 1/2 times a minus 3/5 gm squared over r. The minus signs cancel, and we end up with the 3's also cancel, and the halves. So you get kt over mh, and we can bring over one of those capital M's so that on the right hand side is just gm divided by 5r. Okay? And then all we need to do is solve for T. So this gives us the temperature is G big M little m, mh, over 5K R. Okay, and that's it. Now let's look at 1.8. 1.8, we are already given the formula that we're going to plug into, which is above from 1.7, the formula for the temperature. And here it's just a case of plugging in numbers. And I ask this because, as you'll remember from the problem classes, I'm very keen on you showing all of the units and actually doing a dimensional or a unit analysis showing how you end up with the desired unit, which in this case is a temperature, so you should get kelvins. So not only is it important to plug in the numbers, but also the units. And you'll be marked off, and in fact you'll see in the solutions that I give 1 mark for the value and 1 mark for showing the unit analysis. So it's important. All right, now it's also useful to, instead of just immediately plugging in the numbers, to actually show the formula to make sure we know where you're plugging in. And G is 6.67 times 10 to the minus 11. And this is in units of joules times meters, kilograms to the minus 2. Then we can look up, this was for the mass of the sun. So we know that one solar mass is 2 times 10 to the 30 kilograms. Okay. And then we have the mass of hydrogen, which is 1.67 times 10 to the minus 27 kilograms. Okay, and then in the denominator, we have to put in the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules Kelvin to the minus 1, and then the radius of the sun. So 7 times 10 to the 8 meters. All right, now we could see that the meters cancel. The kilograms also cancel, because we have kilograms times kilograms to the minus 2. And joules cancel, and then we've got the inverse of k to the minus 1, which means that we do end up with Kelvin, so that's good. And if you plug all those numbers in, you should get 4.6 times 10 to the 6 kelvins. And also notice that I'm expecting 2 or 3 significant figures. I don't want 4.678325678910910 because we don't even have that accuracy in the values we're plugging in for the constants. And even if we did, it's not relevant. So try to keep it to 2 or 3 significant digits. All right, the other part of the question, which I should go back to, is comment on why the constant density model is unrealistic. Well, that's a pretty easy one, because we know that in the core, it is much higher density. So we can just write out that one of the questions is, how do we know that? One of the ways we know that is from the detailed modeling. So you could write that. Okay. And good. Then the last question I wanted to look at in detail in section A was 1.6. And this is useful because it's one of the describe type of questions where you then also need to write out full sentences in English. And I will be a little bit harsh if you don't have any grammar, if you don't actually write sentences, if it doesn't make any sense. So please try to have coherent sentences. And the question is asking to describe why numerical modeling requires both outward and inward integration, and what is an iterative method that you can use to minimize the difference in the values. So this is already telling you that you should be getting possibly quite different values depending on which direction you are integrating. All right, so 1.6, well, first of all, how do we do these calculations? We have boundary conditions where we could start at the center of a star and define the central pressure, the central temperature, and then we can use the equations where we keep updating those values as we basically add them up going in the outward direction. And then we should reach the surface at some point, right? Now, the values that we get at the surface, however, may not be realistic at all, because we also know, say, what the pressure should go to zero at the surface, and the temperature we should know is much lower, at something like 5,600 Kelvin or so, and so it needs to also match those boundary conditions. So we can say then that if we set the central values so that they, well, what are the values? Values of pressure, PC, and the temperature, TC, and then we integrate outwards. To the surface. It's pretty unlikely that the values that we chose will actually match the surface boundary conditions. Values that match the surface boundary conditions. Okay, and the same is true if we do the opposite. If we start at the surface and we integrate inwards to try to get the central boundary conditions. Okay, I've started to run out of space, but the second part of the question is asking for the method that we can use to, I believe, well, let's look what it's asking, to iteratively minimize the difference in the inward and outward calculations. Now, I'm not the best with my handwriting, as you know, and also not writing super fast. So I think you get the idea of what I want you to write down. I'm just going to say it in words, that the differences between the inward and outward values of uh, four different values, pressure, temperature, luminosity, and radius, at a midway point in the star can be minimized using the partial derivatives that we estimate. And these are the derivatives in the difference between the inward and outward integration. And then we solve for the boundary values that would then be slightly different. And we need to iteratively do this because we won't immediately get the correct boundary values to start out with. So again, the central pressure and temperature and the outward, say, luminosity and radius. So we need to